it's a pleasure to have Raymond Yeh give our colloquium talk today. Ray was an RA. Yep, thank you. Sorry. So the mic is unmuted now, so be careful what you say. It's a pleasure to have Raymond Yeh give the colloquium today. Ray was an RAP at TTIC a few years back. He since then he has been a faculty member at Purdue. He has, since his PhD, worked on both understanding various fundamental properties of neural network models and injecting or forcing them to have various desired properties and, I guess, not have undesired properties. And I think some of the stuff he'll talk about today is in that vein as well.
Oh, very good. Thanks for the introduction. So today my talk is going to be on computer vision beyond task performance. And it's good to be back at TTIC as always. Yeah, so let's start with progress in computer vision. Over the past 5, maybe 10 years, computer vision has got pretty good in the sense that if you look at SAM3, right, with these perception, on the perception side, you can give a text query and it can now kind of do instant segmentation, essentially, based on text, and it's pretty accurate. And on the generation side, we also got really good, right? This is Nano Banana from Google. Essentially, all kind of low-level image generation, I would say it's basically solved to a degree. And what's even more impressive is you have all these isolated systems, and now they can basically hook everything up into a single VLM. Now, instead of having and knowing how to specialize and operate on an individual system, you can just use natural language queries to get the machines to do what you want. So all this progress is great, and the main kind of driving factor or approach behind it is lots of high-quality data and lots of GPUs. Right? My students go to internships, and then they come back and be like, how do I do internship now? And obviously, we still need great researchers to train these models. Right, so that has essentially summarized, I would say, the main bulk of the mainstream computer vision these days. So, as a researcher, we essentially need to think about, okay, what is next, right? Should I just keep doing this scaling approach and just send my students to internship, or should I think a little bit further down the road on what I should do? So I have been working on 2 areas that will not get there from scaling. So the first direction is robustness with respect to geometric transformation. So we're designing these specialized equivariant deep nets where the output is kind of quote-unquote predictable, I'll define that later, when the input undergoes some kind of geometric transformation. Right? So you will not get that guarantee from scaling. And second is on model immunization, is how can we mitigate the potential risk of having powerful pre-trained model if we want to open source it. Right, so these are the 2 directions, and let's delve into each of them. So the first part of the talk is essentially going to be about equivariant deep nets, and a majority will be surrounding, the technical content will be surrounding our recently accepted CVPR paper, and the work has been done by my student, Ashik. So the way I'm going to present it is I'm going to tell you the origin story on how this research got started, and it started all the way back in my PhD times. So, during my PhD qualifying exam back in 2016, we were discussing VGG networks, right? You have these conv layers, and you downsample, conv again, downsample, and repeat. In the end, you have your classification model output. And in my committee, right, they're mostly consist of signal processing faculty members. So they asked me a very insightful question: is why don't people do anti-aliasing in convolutional neural network? Right? So you have these downsampling layers. How come it's not mentioned that you should do some kind of anti-aliasing? So just a brief background about what is anti-aliasing. So in signal processing, the signal needs to be sampled at a particular rate. Otherwise, things like this could happen, right? The car is going forward, but because of the sampling time, you can actually see the wheels seems like it's turning backward. So why this happens is because your signal, right, are sampled at specific points, these discrete points, but you can have multiple frequency that matches these evidence exactly, and essentially kind of frequency is kind of alias into another frequency. So from classic signal processing, they tell you, right, this Nyquist-Shannon sampling theorem said you need to sample at least twice at the maximum frequency to get perfect reconstruction. So that means if you're downsampling, what you should be doing is you should cap the frequency through some kind of low-pass filter. So you can either blur it, or you can go to the frequency domain and then erase all the high frequency. So this is anti-aliasing. Okay, so now going back to deep nets, right? How did I answer that question back then during my qualifying exam? I was like, no, people know about anti-aliasing, right? They did average pooling. Look, Yeh and Kuhn did this in 1989. So why is average pooling anti-aliasing? Well, you do an average filter, and then you downsample. So that is classic anti-aliasing. And how come it's not popular? Well, in 2007, right? This is also by Yeh and Kuhn, right? They have max pooling, and essentially you can think of this instead of an average filter, you do a max filter, like max sliding window. So increase in 2x2 window, you take the max, so this will be 7. You do a sliding window max, and then downsample at each of the interval of 2. Okay, so my answer was empirically max pooling performs better than average pooling. That's kind of what has been demonstrated, and people have been doing max pooling since. Until recently, I think it becomes less and less popular. I think this answer convinced them, because that's why I'm here. Otherwise, I would not pass my PhD. But it was brought to me that this is an empirical observation, not very satisfying. Can we think about it for more? And once again, this kind of research went on. In 2019, Richard Zhang published a work called Making Convolution Neural Networks Shift Invariant Again. And they proposed what's called a max blur pool. So instead of doing one or the other, just max pooling or average pooling, what you should do before you downsample is you should do a max pooling of one starting one, and then blur, then downsample. So you do need some kind of anti-aliasing, but you should also do max pooling. And their justification for having this design is that it makes the model more invariant or stable with respect to shift. So here, this is from Richard Zhang's works, right? They did a diagonal shift on this image, and they're showing the visualization of the predicted probability at the output with and without anti-aliasing. And you can see the output of anti-aliasing is, an anti-aliasing model is much more stable. And here's another example. Once again, if you read their paper, it is also an empirical observation. So back then I was thinking about this and be like, why is anti-aliasing and shift invariance related, right? One seems to be making a statement about reconstruction. The other one is making a statement about stability. So we want to kind of go a little bit deeper into a definition of invariance and equivariance and see whether we can establish that relationship in a more formal way. Okay, so equivariance, let's start with the definition. A function f of w is equivariant with respect to a group G if for all x and for all little g in that group, you take x, feed it to your model, and then you apply, and you get the output, and you apply a group transformation on x, and then feed it to this model. You will get a output, right, that is transformed by the group action rho y of g. Right, so it's kind of equivariance is equal. These are equality statements about a function f of the w that we're designing.
Sure.
Yes.
Why does it have to be a group?
So you mean in this statement? So in the case if it's not a group, you essentially have like information loss, and you will not be able to have such guarantee. Imagine, let's say you don't have like a circular shift. Instead of you do have a linear shift, then you have to deal with loss of information.
But if it's a field, it's not enough.
Let me see.
If
Possibly can be generalized.
It has to be closed on the transformations.
Yes.
Okay.
So there is some details on why. I think a lot of it makes kind of the math nice.
Okay.
In terms of the design choices. But yes, it can be generalized. So for the most motivation for shift invariance, we take your image x, feed it to your deep neural network, you get an output y, and then you apply your transformation. In this case, it's a circular shift, right? So conveniently, I use a white background, so it doesn't cause an issue in this case. And then you get the output y as well. And if such an equality statement can be guaranteed, then you say this model is a shift invariant. So in this case, your group action at the input, rho x is a circular shift, and at rho y is an identity function, right? So because y stays the same. And in terms of a shift equivariance, right? So this is just I'm illustrating with a semantic segmentation task, right? You generate this mask. If you were to shift your image, then you expect the segmentation mask to be shifted as well. And if you can essentially guarantee this statement, then you would say the model is a shift equivariance. So in real life, or most application, this equivariance is not satisfied in practice, right? Like it's good, right? Many works have studied these exact equivariance design models, and in practice, your data doesn't have this property, right? It's not satisfied. If you can think of like ImageNet, a lot of time the object is already in the center of the image and not at the bottom left. So you may not want to kind of have this shift invariance property exactly. And here I'm giving an example, right? Sure, your camera is moving along with the subject, but the background is changing, right? It's not an exact strict circular shift, and you do have kind of loss of content at this boundary. So you want something like a shift equivariance property, but not exactly. And even in the original case by Richard's own, right, he's not using the definition of shift equivariance as like a strict definition, but like it's kind of like you encourage the output to be somewhat stable. So you don't get the equality guarantee. You just want it to be kind of closer under transformation. So our research started to think about, how can we design deep nets with soft equivariance guarantee? And this will actually link towards the anti-aliasing I've previously motivated. All right, so that leads to our work on CVPR 2026. We first need to define what is an equivariance error, right? So the first thing is, for most relaxation, okay, if I want equality, I'm going to relax it. You do a norm difference, right? So instead of saying this left-hand side and right-hand side needs to be equal, I'm just going to minimize the difference between them. However, this definition has somewhat of a trivial solution. Is I can just, if I put a constant here, I will just put a scaling constant on f, and then I can essentially satisfy arbitrary by scaling it down. So by scaling the function down. So what we actually end up defining is we want to control kind of this deviation, and you still need to normalize by kind of a local scaling factor, which we did by the Jacobian of that function, such that this constant bound actually is a little bit more meaningful, right? So it essentially normalize out that trivial case in the first case. So you take the difference and you normalize by the norm of your input and the kind of the local scaling factor, and it needs to be less than a constant eta. Okay, so I will need to now tell you how do we build these deep nets that satisfy this inequality constraints. So we start simple, right? We did a case study really based on just 1D signal, and then the transformation we're handling here is just a circular shift, and we want it to be invariant. So the goal is to design a soft invariant linear layer, right? So this is the simplest layer that we can have. You can have your input x, which is on an RD vector, and then your circular shift, right? Your group action is just a circular shift matrix over here, and it's a d by d matrix. Here I'm showing for a 4x4 case to apply circular shift on the input. Okay, so with that in mind, your invariance constraint is just f of x is equal to f of shifted x, right? I want this to satisfy for all x. And then your linear layer is nothing but an inner product between your parameters w, which is the same length as x, and then inner product of x. Okay, so this is the toy example setup. Now let's analyze the invariance error. Okay, so we can take the left-hand side, the shifted signal, multiplied by w, subtracted by the inner product between w and x. Okay, and then now I can just factor it out by basic linear algebra. And then we can call this to be essentially a difference operator, right? So we're saying if we were to shift, what is this difference operator on x? Okay, and in signal processing, if you view things in the right bases, it makes the analysis a little bit easier. So this is one of the tricks I learned during my PhD. So in most of the cases, what's a useful basis? You take the SVD. Okay. So if you were to take the SVD of this difference matrix, D is a circular matrix, then U and V actually corresponds to the DFT matrix. Okay. And here we're sorting the bases based on the ascending order of their singular value on sigma, and I just place it on the diagonal. Okay, so with this in mind, let's plug it back in. Okay, so now we can put parentheses around and say you have your W transpose U, so this will just be a Fourier coefficient of W, and this will become the Fourier coefficient of X, and then you have your sigma, which is the singular values on sigma. Okay, so with essentially just some rewriting, I can write it as a summation over your bases essentially over the index of I. Okay, so how can we now kind of control this error? Well, what you do is you can bound this term by enforcing band limitedness on your weights, essentially through a low-pass filter on top of your weights. So what do I mean by that? If your coefficient on W, J, is equal to 0, if it's greater than some cutoff, and how do you choose this cutoff J? It's just your sigma I is greater than some B that you, cutoff value that you want to have. And then what you know is, okay, then I'm just summing from I to this cutoff, and all the sigma J kind of lower than this J will have a value less than B, right? Because I have sorted it. And then I can factor this B out. And then you know that invariance error is less than B times this, essentially the sum of the remaining terms by multiply this B out. And then with a little bit of work, like for example, just use some Cauchy-Schwarz inequality, you can show that the invariance error, once you normalize by the norm of the parameters and X, is less than or equal to some constant multiplied by this B cutoff value that we have chosen. And here, K is a constant that's kind of dependent on the group, right? So depending on what group you have, you will have this additional constant in front of it, right? So the idea is, you have some constant that is kind of intrinsic to the group, but I get to choose what this B is, and essentially limit the band, kind of the frequency in W in order to get your guarantees. Okay, so let's take a look at what's the relationship between this cutoff B and your invariance error. So here on the y-axis, I'm kind of showing this average invariance error on a data set using a linear model, and then we can just choose the number of bases vector we're using, and you can see that when the number of bases is low, the invariance error remains low, and when you start to have more and more basis vector, the error becomes higher. And on the animation side, here we're visualizing kind of the weights of the weight vector using 1 to in total of 16 bases. So as you can expect, right, this is nothing but a kind of the Fourier bases added back together, and so you essentially get more and more oscillation on top of your weight vector. All right, so the story actually, in the end, is quite simple. If you want your exact invariance, in this linear case, you have to have a constant weight, right? Essentially, you have your DC component, you just output everything multiplied by the same value, then there will be circular shift invariance. And the invariance error really just now depends on your cutoff index, like how many bases you want to choose. And you can have a control over this invariance error by choosing this corresponding upper bound. Essentially, if it's band limited by this cutoff, then I can go look up what is the cutoff you can have from this layer. Yeah. So obviously, if it's just for shift, it will be not very interesting. So we can go beyond shift, right? So you can generalize to any discrete group. What you will do is just replace the S, right, with the appropriate group action to compute that for a difference D, and then we can also generalize to compact Lie groups here, right? What you would do is replace S with the Lie algebra representation. Yes.
So just to recap, the assumption, the framework, the scope of this is that you have a linear layer which maps some vector to a here.
Currently, so the toy example I explained is scalar. In the paper, we needed to make it work on vectors.
So if you map a vector to a vector,
Yes.
then can you just hint like what changes? So now you have
It's basically very similar. So in the vector, it will be an equivariance statement, right?
yeah.
And then what you will do is basically there's a trick like a
But
tensor.
is there a tensor instead of a matrix now?
Yeah. So what you can do is I'll get to that. There's basically
Okay,
a tensor vector representation that you can.
If you get to
And then we can generalize to other essentially linear operations such as COM or MLP, and it, obviously it will also support things like bases, which are just like a bias term, such as a positional encoding, because these are linear.
So, but in the context of a transformer,
Yes.
should I like there are linear operators for the the computation of the attention elements, and then there is a MLP sitting on top. Should I think of all of this as individual?
Yes. So you will basically take each of these layers and then essentially force their weights to be band limited. Each of the components. You have to do that everywhere.
By some B.
Yes.
B but now I have a cumulative effect.
Correct. And then we can show that how it accumulates. Yeah. In practice, let's just say it this way: the bound will give you very loose once you start accumulating. So the bound itself is not practical, but it gives you a kind of a good design that we will validate empirically. Yeah. So I'll say maybe the design is theoretically inspired, if that's the right way. Okay. So given a group, right? And then let's say we're doing it with let A be the algebra representation. You will take this SVD and sort it, the same procedure. And then how do you design this projection operator? Well, it's just you take your B and then take these bases vector. And then you essentially start cell based on the constant that you choose. And then a soft equivariance layer is defined by doing this projection first onto W, and then that is your generalized version for your linear layer. And then we can go from invariance to equivariance, right? In the case where your weight is not a singular scalar output, what you will do, this is actually common, is you can rewrite a equivariance statement into a invariance statement using a tensor product representation. So in this case, you have your S. We can go. I will not go into the details of this, but you can write it as a tensor product representation, and you will have a kind of like a bigger S that solves for the same thing. So the idea is essentially you flatten your weight vector W into a vector, and then you essentially follow the same procedure. Right. So in the paper, there's some details. Right. This SVD could be expensive because you're flattening something that's like quadratic on top of a quadratic again. So it could be expensive. So we have some speed up tricks that you instead of doing SVD, you do a kind of a Schur decomposition, which is a kind of local decomposition on top of that matrix. So I think that's kind of going back to Greg's question. How we will do it, essentially you can convert that to a invariant setup where you have a vector and everything else follows. So let's take a look at how, in practice, how this works. Right? So you have your VIT. Here we're visualizing the patch embedding, and the symmetry that we're dealing with is 90-degree rotation. So your weights will look something like this. If you want it to be perfectly equivariant, right? These are 90-degree rotation. Your weights should look exactly the same. So your patch embedding should look exactly the same if you were to rotate by 90 degrees. And that's why you see this like kind of really nice symmetry when it's perfectly equivariant. And as more and more bases you add, right, it becomes non-equivariant, and you can get to control kind of going from left to right. And you can see, right, these are no longer, the symmetry no longer appears. And here we're visualizing the activation output, right, of these two cat input. And you can see here they look perfectly equivariant. When you rotate it, the activation, not so much on the very right-hand side. And here we show the equivariance error. So if you were to enclose it exactly, your error is 0. Otherwise, you see some differences.
This is just the very first layer in VIT which embeds.
Yeah, so you have the patch embed. Yeah, that's why. That's why it has nice visualization. In the end, it becomes harder to see it. Yeah. Okay, so this kind of gives you the kind of nice intuition that we have a mechanism now can go from perfectly equivariant to all the way with all your degree of freedom. So in practice, what do? we can actually adapt existing pre-trained model. You take a trained pre-trained model. We do not need to train from scratch, right? It's not like a very specialized architecture. In many of Equivariance where they have their own architecture, and you can't really take a pre-trained model and do and use it. So for us, the good case is you can take this pre-trained model and just do a projection on your weights. However, because it's nonlinear, you do need to perform supervised fine-tuning. So what is nice about this approach is if you're pre-trained from scratch, that will be my lab for a week. My students really don't like to train models from scratch anymore. So a lot of the research that we do now, we think about how can we leverage existing foundation model. Yeah. So that's kind of the approach. And then let's look at some results. So the first thing we did is we take ImageNet and we evaluate. So we report 3 metrics. The first metric is just accuracy. The second is an augmented accuracy. So we're just evaluating our images rotate plus and minus 30 degrees. And then we measure the invariance error at the final output. Our baseline is a approach called a canonicalizer. So essentially, the idea is they'll have some other network that predicts which kind of orientation or the rotation angle the image is in and try to kind of revert that transformation, which is also applicable on a pre-trained model. Okay, so accuracy-wise, I think we get comparable, slightly better. We evaluate on VIT, Dino V2, and then ResNet 50. On the augmented accuracy, we see a little bit more gains. And we see kind of the best results when we characterize it on the invariance error. Right, all the invariance error will be non-zero because it's a soft on plus or minus 30 degrees. And then we also evaluate on segmentation. In this case, we just picked kind of the simplest one. We did Pascal VOC. Same setup, MIOU, right? This is a standard metric. We evaluate on the augmented MIOU plus or minus 30 degree, and then measure the equivariance error at the output. Baseline is still the same canonicalizer. Comparable, if not slightly better, improved accuracy. Once again, across VIT, Dino V2, and then a seg former. We also see a little bit more gain on the augmentations ones. And then finally, the equivariance error remains competitive and slightly lower. So it turns out some of these models are actually already pretty good without even imposing additional equivariance constraint, but you do see some benefits when we further impose it. So that's the takeaway for the first part is, we present a framework to construct these soft equivariant layers by analyzing SVD of the difference operator, and we can bound this equivariance error and we kind of relate this to the anti-aliasing and hopefully solve my long-standing question back during my PhD. Yes, it's good to do anti-aliasing, and the reason is it's related to this bound on your invariance error. And it's applicable to existing architecture. We do not need to train from scratch. We also have a lot of other equivariance work from my group, mainly by Ashik as well. We are working on scale equivariance, so we also investigate into how we can build models such that if we were to do local kind of scaling, right, this is not a group, right, and such that the performance and the variance on the predicted model, on the output prediction is not too big. All right, so this is a kind of first half. Maybe it's a good time to see if there are any questions.
So on the previous slide,
yes.
The baseline canonicalizer, I guess that's using a different base model?
The base model is the same, but they have a separate kind of a little module that essentially kind of estimates what's the...
So it actually hurts them to try to estimate the image rotation.
Yes, so in the case for... Yes, so actually in this case...
I think almost every case that they're worse than the base model.
So in this case, right, it's really for segmentation because the corners go out of bounds. So there's some trickiness in how to handle that interpolation. And we use their default codes.
Okay.
Currently, it's but for classification, it works. So I think a lot of this has implementation details because how do you handle boundaries? It becomes very tricky. I think there's another question.
Yeah, I just wanted to ask. I think the reason equivariance hasn't caught on in computer vision as opposed to molecular networks and stuff like that is because the models are not really shift equivariant or rotationally equivariant, or
Yeah.
like it's not the same image. I'm wondering if there's a way to learn the group action, and because here you're kind of assuming it.
Yeah.
When it's not necessarily helpful to rotate a horse by 30 degrees.
Yeah, it turns out it's very challenging. I have some earlier works, I think back in 2021, that's trying to discover equivariances. But the main challenge is you have to observe it from data, and your data have noise, right? So how do you, because equivariance is on equality statements, but under noise, how do you know this is noise or is it just deviation from the equivariance error? So you do need to have a little bit kind of a, I would say, it's kind of like a chicken and egg problem, right? So a lot of times this has to be known a priori. But there are existing work that tries to learn these equivariances. Yeah, we can talk offline about that. Okay. And okay, now I'll shift to the second part to start talking about what's modern immunization. So this is a work by my student and Brian Boulin's student, by my student Ija and Brian's student Sita working on this. So this is a work on model immunization from conditional number perspective presented at ICML. And just to know, Brian was also from TTI, and I guess TTI brings good people together. All right, so what is model immunization about, right? So open weight generative AI has got basically really good, right? Whether it's stable diffusion, deployed, right? These content generations, for the average consumer are basically a few prompts away. You can use commercial hardware and then start to generate really good images. Now, if you like Spider-Man, it will tell you that with great power comes great responsibility. If we open source these models, there is the potential risk of being misused, right? So I'll just name a few, right? Whether it's generating explicit AI images, that's not desirable, to more serious things, right? Like potentially faking election photos, or recently those was very popular, like I think last year everyone was generating these Ghibli images. It's great for us, but maybe not so great for the artists, right? So there's some risk of potential being misused. So the threat model that we're considering in this setup is what's called malicious adaptation of open weight models. So we imagine, you have your, people working on these big foundation models want to do good, right? So let's say I accidentally train on these license data, and then they use some learning mechanism to erase this data, and now they have a model that's somewhat safe. Okay, so here I'm just using this guitar as what is malicious, but you can imagine whatever that is undesirable. Okay, so this preacher model is now kind of safe in the mind of the people working on it, and now you can release this. And then immediately what this some backender can do is just use some model adaptation, get some image of this guitar, and then just train it back. And so it's kind of defeats the purpose, right? So this is the setting where doing is if we release the model weight, people with the same capability can try to fine tune on these, so for them to be unsafe. Right? So it's somewhat easy to kind of relearn these concepts. So there are existing works, right? Also from U Chicago as well. They want to protect the data, right? So every time before you release the data, you do some kind of data poisoning, right? So you take your photographs, and then you have your pre-trained model. When you apply to the adaptation, this works. But if you take your images, feed it to some essentially data poisoning techniques, now feed it to the adaptation algorithm, it no longer works. Right? So this is great. Every time you want to release your images onto the internet, right, you add some adversarial noise. Right? So the responsibility of preventing these malicious adaptation is placed on the kind of the content creators. Right? So that's one approach. And in our approach, we kind of think, well, there's the other aspect that you can protect. How about you protect the model instead? So the idea is essentially same setup as before, but before you release the model, you'll run it through what's called an immunization algorithm. Right? So you want to make it more difficult, right, to apply these adaptations on top of the original data. Right? So your immunized model no longer generates this, in this case, the guitar. Right? So the kind of shift in the mindset is we're thinking about whether the model releaser can be responsible for preventing the malicious application.
Does that make any fine-tuning of the model difficult then?
You mean during this immunization process?
If you immunize, right? Yeah.
You mean for other?
Say I wanted to fine-tune this model for via
So yes. So the immunization only aims to make it more difficult for harmful content. So you essentially have to know that ahead of time. Yeah. And for the other stuff, it tries to make it keep it as the same. We'll get to that. Yeah. So the first work we did on this is we just formulated it as some bi-level optimization, right? You think about this as we're meta-learning poor initialization for the adaptation algorithm, right? I make it difficult to learn. So essentially on your upper level task, you have these ways that tries to worsen the performance of your algorithm A, and your lower level task is aims to adapt the model to kind of relearn this concept C over here. And L is just a general adaptation loss function. And here, we use the difference between theta and phi just because sometimes the adaptation algorithm adds more parameters. So we can only update the pre-trained weights. Okay, so the meta-learning setup kind of works. You have your original adaptation, let's say using LoRa. So here we're trying to mimic the Picasso style. Okay, and then if you were to immunize it and you update it running it on the same setup, you can see the performance. I should say on the y-axis is basically the higher the 1 minus L pips, the closer it is to the original reference image. And you can see the performance doesn't really go up. And essentially your gain from having this immunization is this gap between the performance of immunized and not immunized models. And one thing, after this work, I was talking to Brian, he's like, this is really an optimization problem, right? You're trying to make optimization harder. So, well, go back to the basics. Condition numbers, right? In condition number, right, for a general matrix S over here, the condition number defined as kappa is really the ratio between the max and min singular values. And if you take an optimization course, right, larger condition number generally means slower convergence, right? So the idea is, if it's well conditioned, you have a really somewhat nice landscape, and you can do your gradient descent. If it's the condition number is large, what you have is these kind of elongated landscape, and the gradient descent will fluctuate along one dimension and makes convergence a little bit harder. Right, so that was the intuition we started thinking about this. Right, and a constant step size Stevens descent algorithm. Right, if you're minimizing this loss where L is strongly convex, then the Hessian, right, of this loss, right, with respect to the min and max singular value, right, you can get a convergence rate of 1 minus sigma min divided by sigma max over the step size of T. Right, so essentially you can get it bound on how fast you're moving towards your the optimal solution. And our question is, how do I use this condition number for immunization, right? Because we want to make things harder to learn, so that seems to suggest I need to maximize the condition number or some sort. But we need to simplify and make some assumption for this to work. Okay, so our framework for studying is, we have a goal. Here we're assuming that we're learning a pre-trained feature extractor, such that when you fine-tune a classifier h of w, using this feature on the harmful task, it is difficult, but not for any other task. I think this is going back to Matt's question, right? Can I still use this model, or is it just becomes completely useless? Right. And once again, we always start simple linear feature extractor. We're just assuming everything is linear. So you have x of theta over here, right? So it's a linear extractor. You also have a linear classifier that's on top of this feature. So it's kind of like two linear layers stacked together. And you want to learn this harmful task, which you have a data set describing. And then you have another linear classifier g of w, g of omega here. You can think of this as another head that's using this, and it's training on some pre-trained tasks. So these two tasks are different from each other. And we're studying the setting in regression. Okay, so you use your feature f of w, apply a harmful task classifier on top of it, and then do least square. And we're assuming the bad actor is performing linear probing on d of h, right? So it just minimizes the final layer and keep your theta as fixed. So it only trains the last linear layer. Okay, so under this setup, can we make it more difficult to train on the harmful tasks? Okay, so let's now think about the definition, right? It is more difficult to apply linear probing on this harmful task DH when you're using these immunized feature extractor, right? So the other choice is, you can directly use the input data. Right? They can just change their own model, so you want to be more difficult. So what does that translate to a optimization statement? Well, that means you have your loss function on this harmful task, you have your weights of W, and you have your pre-trained extractor theta. The condition number on this harmful task needs to be greater than if you're not using this pre-trained extractor, so we just put like an identity matrix there. Okay? Okay, second statement, it is not more difficult to apply linear probing on other tasks. So in this case, we just say DP, which is your pre-training task, is your other task. So your condition number on the pre-training task, if you're using the feature extractor without it, should be less than or equal to. Right? So it needs to be somewhat well-conditioned and even better than not using the feature extractor. Okay, and the third part is the immunized model should maintain the competitive task performance on the pre-training task, right? So you don't want to lose your capability of classification, for example, or regression. Okay, so now if you have these three objectives and then you have these three statements, well, we can basically try to come up with an optimization problem to learn the pre-trained feature extractor to optimize theta. Okay, so this leads to this optimization where we're minimizing over W and theta, where we have a first term that is trying to immunize the model on harmful tasks. So this is the Hessian, and this H over here is indicating it's the Hessian of that loss function on the harmful task. And this is dependent on theta, right? Remember, the task for the harmful task that's doing linear probing now is a function of your pre-trained feature extractor theta. Okay, so it's a function of theta. Okay, and here we propose, right, to do this kind of regularizer that's making S ill-post. So we want to make the condition number for the Hessian of this H on theta to be ill-post. Okay, so the way we propose, we just do 1 over, right, the Fourier's norm on S, and then subtract by the smallest singular value. So if you can kind of see this, if you minimize over here, you're making the denominator bigger, and this first term is just related to the maximum of the singular value. So you're trying to make the max and the min of the singular values to be big, right? Which makes it ill condition. And to make it well conditioned, essentially you flip it around, and then you want to maintain it on the other task. So condition on the pre-training task, right? You want to make it well conditioned. And finally, you have your standard loss that maintains the model's performance. Okay, now the question is, how do you solve this optimization problem? We go to gradient descent. So you just solve it using gradient descent, you do gradient update, and optimize it. And one thing that is very crucial when you work with optimization folks, they want to make sure the optimization objective is somewhat quote-unquote nice. So they want to make sure, right? Okay, we come up with this regularizer that's encouraging to be ill-post. Is this a reasonable regularizer? Right. So it turns out that you can actually upper bound it reasonably when it's reasonably away from infinity. So it means that if you're optimizing or minimizing these R ill, then you are actually making your condition number actually worse, so larger. And then it turns out this is different. This regularizer is differentiable. We have a nice analytical form. And then if you choose your learning rate correctly, you can get monotonic increases in the condition number. All right, so that's all to this approach is we're essentially training these pre-trained feature extractor such that for some tasks it is hard, for some tasks it's easy. Okay.
So presumably there are some combinations of harmful and safe tasks definitions that where it is not possible to do, right?
That's correct. Right. So imagine, so it really depends. If it's all linear, it just depends on kind of the angles between their singular values. So imagine you just have your harmful task and your pre-trained task to be exactly the same.
That's an extreme case.
There's no way to separate them out. Right. So as long as there's an angle between them, there's a way to do it. Yeah.
And this is sort of, this will try to minimize that function, but is there a guarantee? I guess.
No, there's no guarantee. Yeah. But yeah. So that's why we'll show it empirically that it actually did make it more difficult. Yeah. But
is there a way to judge before trying to run this, somehow by looking at the weights or something like that, whether it is a worthwhile like here's the definition of a harmful task, and you look at it and say, oh, I think it's not going to work because it's too close to the core safe task.
Yeah, I mean, I think it will have to be some kind of heuristic, because how do you compute it without computing it, right? So we have not looked into that, but I think it's possible, right? You essentially need some kind of similarity metric between the distribution and say the harmful task is different enough.
Yeah, and you can sample it.
And and then you can estimate it. Okay, so let's go into experiments. Evaluation metric, essentially we came up with what's called a relative immunization ratio. So the idea is you have two terms. The first term is saying on the harmful task, did you make it worse, right? So it's the ratio between the condition number, and you divide it based on the ratio between the pre-training task, and did you make it worse for the second part? So ideally you want to make the numerator large and the denominator small. And we have some baselines. So baseline is we just directly immunize this model based on the regularizer. The second ones we also did EMA. And finally, what is interesting is, in PyTorch, turns out condition number, they give you some kind of approximation for gradients. So it'll give you a backprop number. So that's what we use. So here we did it on kind of the most classic regression task on house price data sets. And then what we show is we can get really good ratios in terms of the immunization ratio. So here we also pictorially show that that from the convergence terms we can indeed make our convergence fast. So in this case ours is right on non-harmful tasks. It's basically the same as it's better than identity, right? Identity is this one. So we can actually make it better to better to optimize on pre-trained tasks. And on the harmful task, you can see ours is all the way at the top, so you can get your slower convergence compared to the identity widgets. So this is desirable and show that we can indeed make gradient descent harder on harmful tasks and not for other tasks. We also did this for an MNIST classification. So here we show the immunization ratio just pictorially. So here we just choose different pairs of the digit and say this is harmful, this is not harmful, and then repeat. And long story short, blue means it's good, where the immunization ratio is greater than 1, then everything works for us. So one thing that was, everything was linear, not very exciting. So we ran some experiments on deep nets. So we did pre-trained ResNet and VIT, and the only thing that to pay attention to is the evaluation metric now has changed. Instead of comparing relative to the identity for a feature extractor, we just compare it to the pre-trained model. Right, that's the most realistic setting. You compare whether your effectiveness of immunization compared relative to your pre-trained model, and the rest follows. And then we also report the task performance on accuracy. Okay, so classification and task. Here I won't bore you with all the numbers. Just trust us. We maintain similar accuracy and get better immunization ratio. So just on both ResNet and VIT. So it seems to be effective across two architecture and across two data sets. So takeaways for this part is just immunization, right? We talked about this paradigm to protect kind of malicious application, and then model releaser can now be responsible for sharing some of the responsibility. And we view immunization from a conditional number perspective. So it's no longer just some meta-learn. Now we can say, oh, we actually made condition number worse, and that's why it's harder to converge. We also did a lot of other immunization work within my group. So we also did on few-shot classification, how do you protect that, and also generalize it to multiple concepts. So right now, all the experiment I've shown here is kind of like one data set, one group, but what happens if you do it like sequentially? You have multiple concepts that you want to immunize. So we also have some thought into it. Okay, before I go today, once again, I still have my self-promotion slides. I'm still not tenured yet. I'll still talk about this. So first thing first, Ashik and Ija are graduating, so we are looking for new members to join lab. I think most of the TTIC folks are already in PhD program, but if you know anyone else, reach out to me. And our group has a lot of other cool works, okay? Besides immunization and equivariance, it's not always this mathy. We just had our first robotics paper that was working on semantic representation in 3D. So we essentially want to embed semantic information into Gaussian splats. We also did a 4D generation. Well, this was a collaboration with Snap from the internship work. We also did a lot of classic computer vision, such as facial landmark detection, anomaly detection, and then symmetry detection, right? All the detection segmentation you can think about. We have some forms students really like to apply to applications. And finally, we have many more. So I encourage you to look at my website, raymond-yeh.com. And finally, this is the work that I collaborated with Rana a while back, where we use diffusion model to generate ambigrams. So ambigrams is just text that can be read upright and rotated. Fits nicely with the equivariance symmetry line, and this says ask. So I think it's now a good time to ask me whatever questions you have.
We do have some time for questions.
So for the for the immunization work, how difficult is it to identify the weights for the 3 loss terms?
Identify the weights. You mean when we train it, or
So you have this, your losses is weighted sum of 3 terms.
yes.
So how hard is it to choose?
The balance between them.
Yeah.
It requires hyperparameter tuning. I think the essentially we monitor, right? It's the standard hyperparameter in practice. You monitor the immunization ratio, and then you hyperparameter tune based on that on the validation set.
Do you have a sense of how they generalize the different data sets?
You mean the hyperparameter?
The hyperparameter.
I see. My understanding is it requires tuning.
Okay.
Different
It's not.
data sets or different definitions of harmful tasks?
I guess either.
So it generalizes across data sets to a degree, because for MNIST, this is all run basically the same. We didn't do hyperparameter streets across all combination of MNIST. So I think across the architecture, the hyperparameter transfer, but like let's say on this MNIST versus the ImageNet, you cannot use the same hyperparameters. So the balance changes. And this has to do with, because if you look at this term, right, this term has to do with the loss, right? So depending on how difficult this task is, your weighting needs to be different.
Yep.
Yes.
So since you've had multiple, like MNIST and some other classification tests, the definition of harmful there is a particular category of errors?
We just said digit 1 is harmful, and remaining are not harmful. Like, it's just a choice.
But this is not generation.
Right, it's not generation. Everything is classification. Right, so in this setting, we did it for classification.
So I guess so what does it mean to immunize an MNIST classifier against digit 1? I guess
when you fine-tune, when you use your pre-trained feature extractor, and you fine-tune on MNIST of digit 1.
Oh, you never output. So if you see 1, you should misclassify it as something else.
Correct. Right. But it's not really misclassified. It's just it's more difficult to optimize it. Like the loss decreased slower. That was the right.
No, but like the ideal solution to immunization problem there is that if you succeed 100% in some sense, then whenever you see digit 1, you would not classify it as digit 1.
I see. So you're thinking in terms of the outcome of the model.
The definition of the task.
Right. So the way we define it is just it's difficult to optimize. So you start from your pre-trained model, which has some performance, and you want to fine-tune on this new task. And if you just didn't optimize the weight, right, it will give you 1 performance.
So it's a difference between classification accuracy on all the other digit versus 1.
Yes, that could be the way, but we didn't define it like that. We defined it based on essentially how fast it converged to what it could be. Because eventually it will get there. Like if you let's even make the conditional number, it will get there. Yeah. Other questions?
All right. Thanks again.
Thank you.